Welcome back. So far in our lectures on ordinary differential equations, we have looked at what's called first order ODEs. That is, we looked at ordinary differential equations where the left-hand side, for example, can be isolated as y prime, and on the right-hand side, we have simply some function of t and y of t, right? And for example, one differential equation we looked at in the past is dy dt equals negative 20y, right? Some exponential decay. And we then took this ODE and developed what's called Euler's method, Runge-Kutta methods, and we looked at how to use MATLAB ODE for 5 function to solve this differential equation, right? And everything worked out really nice because whatever equation we were looking at was always expressed in this form. So we can directly discretize dy dt, let's say with a finite difference approximation, and once we have that, it's easy to see how Euler's method falls in place. How about, however, if we have a higher order ODE? For example, here is an ODE that has second derivatives, right? 2y double prime means the second derivative of y with respect to t minus 5y plus y equals 0. Here we have higher derivatives, which, if we remember Euler's method specifically, the method that we developed before doesn't really lend itself to solving an equation like this because we have y double prime here, right? So what to do in this case? And this video covers what to do in this case when we have higher order ODEs, and simply what we're going to do is learn how to convert this higher order ODEs to a system of first order ODEs. So let's look at this particular example that we're just talking about now. So let's look at the following initial value problem where we're giving a second order now ODE of the type we just mentioned, minus 5y plus y equals 0. And of course this is an initial value problem, so let's give some initial values for y3, for example, equals 6, and y prime 3 equals minus 1, right? So here we have our famous initial values, our initial conditions. So let's look at the technique of changing these variables or calling them something slightly different. For example, let's call x1 of t, let's call that y of t. And let's call this other variable x2 of t, let's call this y prime of t. If we take this now and differentiate these variables with respect to t, we have x1 prime of t, which will be y prime of t. And we'll have now x2 prime of t will be equal to y double prime of t, where we can take y double prime from this definition here, right? So, for example, we can take this equation here and rewrite it slightly so that 2y double prime equals 5y prime minus y, right? And we can divide both sides by 2, so y double primes go to be 5 over 2 y prime minus y over 2. And if you notice, y double prime is exactly what we need to define the variable x2. So let's plug that in here, and we'll have that this quantity will be 5 over 2 y prime of t minus 1/2 y of t, right? Which now what we're going to do is use the definition that we just have here, where y of t is just x1 and y prime of t is called x2. So let's substitute into here, and we're going to end up with 5/2 x2 of t minus 1/2 x1 of t. right? So now we have rewritten this entire system here, this second order ODE into a system of ODEs, and let's write this down explicitly, where we have x1 prime, which will be equal to x2, right? So because y, so x1 prime is y prime, but we already declared y prime to be x2, so I'm just plugging this in here. And x2 prime equals 5/2 x2 minus 1/2 x1. Right? And of course we have still our initial conditions, which will be x1 of 3 will be 6, and x2 of 3 will be minus 1. That's copied straight from this part here. And so what we have here now, which I'll try to highlight here, we have rewritten this original problem, which was in this form, into this form now. And as you can notice, now we have two equations, right? We have x1 prime and x2 prime, but the right-hand side of these equations, right, they depend on only x2 and x1. In other words, we converted a second-order ODE into a system of first-order ODEs, and the system has the same, initial values as the original problem statement. But once we have this here, we can more easily plug in Euler's method, right? So let's look at another example, just to bring this message home. Let's look at the following ODE. So let's look at example 2, and here is going to be our ODE. Right, so we'll have y 4 prime plus 3y double prime minus sine of t y prime plus 8y equals t squared. This is just an example, right? There's nothing special here. We kind of chose this example at random just to see how to do something more general, a little more complicated, to take that technique and generalize it a little bit. So, and of course we have all of these initial conditions, right? So we're going to say that y of 0, let's say it's 1, y prime of 0 will be equal to 2, y double prime at 0, say it's equal to 3, y triple prime of 0 will be equal to 4. Right? Let's do our change of variables, right? C of e. And let's call, following the technique we just developed, we call x1 to be y, x2 will be y prime, x3 will be y double prime, and x4 will be y triple prime, right? Third derivative of y. Of course, we can do the same thing as we just did before, which is compute the derivative with respect to time of each of these variables, and we're going to end up with x1 prime equals y prime, x2 prime equals y double prime, right? Essentially, we're taking the first derivative of all of these parts, so let's just write it down. x3 prime is going to be equal to y triple prime, and x4 prime will be equal to y 1, 2, 3, 4. Right, so we have now rewritten this ODE, which was, had 4 derivatives before, so it's not a first order ODE anymore. But now we have rewritten into a system, of first order ODEs. And here's our system. x1 prime equals x2. Right, why is x1 prime equals x2? Because we declared that x1 prime is y prime. We just differentiated this part. But we see that y prime is also x2, so I plug in the value there. And similarly, we can see that for the other equations, we have x2 prime equals x3. And we have that x3 prime equals x4. And now x4 prime, right, which will be this fourth derivative variable. Well, the fourth derivative appears here, so all we have to do is move everything to the other side with t, and that's going to be equal to t squared minus 3x3, right? And I'm already going ahead and plugging in that, that y double prime is x3, right? So that's where we got this from. So I'm already plugging this in, plus sine of t times x2. Similarly, we made that substitution there, minus 8x1. Right, and let's write what our initial variable, our initial conditions are. x1 of 0 equals 1, x2 of 0 equals 2, x3 of 0 equals 3, x4 of 0 equals 4. Right, so here's our solution. We converted this complicated looking higher order ODE into a system. Right, we have 4 equations here, 4 first order ODEs. And if we were going to code this in MATLAB, right, so this is a pseudocode, right? Pseudocode just stands for, you know, some loose ideas about how to code this. So let's write this pseudocode. In this case, we will create a vector. We call this the vector of initial conditions. We can call this x naught, right? That will be a variable 1, 2, 3, 4. That will be our initial vector. And when we declare a function, which will, you know, say that our function dx dt, we'll call this something else in MATLAB, but it will be a function, right? We can declare an inline function in MATLAB, for example, with this syntax, right? Which will be here our x2, x3, x4, and this is going to be that remaining part, right? Minus 8x1 plus sine of t, x2 minus 3x3 plus t squared. Right, so that's how we declare this function, where again here x is our belongs to a set of real, it's a vector of 4 dimensions, right? And so what we have is, for example, when we start at initial conditions, let's say we start at t equals 0, and we plug in x0 into you know, our initial conditions into this function here. So we're going to have that dx dt, right? X being our entire vector now is going to be 2, 3, 4, minus 17. If we plug that in, make that calculation, you'll see that's the case. And let's say, you know, let's choose a step size h equals 1. We'll have that x at 0 plus h, right? Let's take an Euler step. That will be x0 plus that vector we just computed, dx dt times h, right? And our solution basically will be expressed with this vector x, right, belonging to set of real numbers in R4 that gets evolved over time. So this is a summary of how to convert higher order ODEs, converting them into a system of first order ODEs, and how to use basic Euler's method to solve it.